Hello everyone, thank you for tuning in. Today we're going to talk about Math 121, section 1.3. This section deals with collecting sample data. So first, we have two definitions that are hand in hand. The first is experiment, which is a treatment is applied and the effects are recorded. So we're doing something called a treatment, and then we record the effects. That's an experiment, right? You do something, you see what happens. You do something, you see what happens. Experimental units or subjects are what's being experimented on, are the things being experimented on. Experimental units are subjects. Subjects, people. Experimental units, inanimate objects. Observational study, that is different than an experiment. Here you're not doing something, you're just observing. So we observe / measure, depending on what you're doing, without, I abbreviated, without attempting to modify these subjects. We're just watching, right? We're just observing. We're not doing something. If you're doing something, you're doing an experiment. If you're just watching, you're doing an observation. An example of that, ice cream and drownings. So observationally, we see a direct increase in ice cream sales and drownings at the same time. We see a direct increase in ice cream sales and drownings at the same time. So, the more ice cream people are buying, the more people are drowning. So ice cream causes drownings. That's an observational study. That conclusion might be flawed, though. So what's a better way to get the data? Maybe instead of observing, we do an experiment. So for an experiment, we give 100 people ice cream and 100 nothing, and record no difference in drowning rate. So here, we fed a bunch of people ice cream, we fed a bunch of other people nothing, and we noted, was there any difference in the drowning rate? Yay or nay? Turns out no, because does ice cream cause drownings? No. What's the hidden factor here? When do we buy more ice cream? In the summer. When are people more likely to drown? Also in the summer. Does that mean there's a direct relationship between the two? No. So make sure you note that observations can't always give you the best data. So experiments are generally better, but not always. If we wanted to think of an example where an observation is better than an experiment, let's say you're recording animal behaviors in the wild. Doesn't make sense to bring them into a lab and run an experiment on them when you are just recording the behaviors in the wild, right? Now, in designing experiments, we want to keep three things in mind. First is replication. We should repeat experiments multiple times. Repeat experiments to verify results. Maybe the first time you did something, it was a fluke. You never know, right? So you should repeat it. You should replicate it. Studies should be repeated. The more you repeat something, the more definitive your results can be claimed to be, right? Blinding. Blinding happens when the subject does not know if they are in the experiment group or the control group. What's a control group? Well, if you don't know what a control group is, think about it like in the ice cream example. The control would be the 100 people I did nothing to. That's a group to see the base effects without any experiment being done. The experiment group has something done to it. The control group is just monitored to get a baseline effect, right? So blinding, you don't know if you're a subject, you don't know if you're experimented on or not. And this is because of what's called the placebo effect. This is subjects reporting changes without the effect of the treatment. This is really common in medicine. A lot of times in medicine, they give 2 different pills to each group. One pill gets the medicine, and one pill gets what's called a placebo, or a fake pill, usually a sugar pill or a salt pill or something like that doesn't have any medicine in it. And then you notice the differences in who got better. Unfortunately, that limits the experiments a little bit, because the placebo effect means just thinking you're getting medicine, you don't know if it's a salt pill or a medicine pill, right, might make you get better. That happens a lot in medicine. We have a placebo effect where people get better without actually receiving anything for a treatment. Now, a double blind is when neither experimenter nor subject know who's in which group. Neither subject nor, I'm going to use the word tester, knows who is control versus experiment group. Experiment group. Neither person knows who's being tested on. This is to prevent bias. If I'm the tester and I don't know whether my subject has the real medicine or the fake medicine, there is no way for me to influence the results, right? And that happens a lot in clinical trials as well, double blinding. A great example of a failure to double blind, there's an episode of House where one of the doctors prevents or causes medical fraud to shift a person from the control group into the experiment group because of his personal feelings towards that doctor. Obviously, not okay, right? We need to be rigorous and very strict in experiments to make sure the data is accurate as possible. So double blind is another common technique. Neither the tester nor the subject knows who's being experimented on. Lastly, randomization. We should always assign people to groups randomly. We should assign groups randomly. For example, you want to take a experiment with 100 people. Don't give the first 50 people the medicine and the second 50 people the placebo. Because maybe the people who show up first have personality characteristics or chemical differences in their brain. That's why they showed up earlier first. That would have effects on your study. You don't know what might affect your study, so you should assign people randomly to their groups. That's, once again, to prevent any potential biases or extra effects from taking place. So randomize when you can. Now, that's for designing experiments, right? What about actually collecting our data? Well, we're going to have 5 definitions here. The first one is going to be the ideal, and then the other 4 are going to be additional types. So the ideal way to collect sample data is with a simple random sample. Here, every group of some number of subjects, let's say n, maybe it's 50 people, every group of whatever size, n is the size of the group, right? Maybe it's 50, maybe it's 100, who knows? Every group of n subjects has an equal chance of being selected. Every possible group you could form is equally likely because it's random. What's the chances any individual group is formed? Well, if you're doing it completely at random, they all have the same chance. That is not true for the other sampling methods we're going to look at. This is the best way to collect data. The book calls it the gold standard. The best way to collect data is with a simple random sample. Every group of whatever size you're looking for has an equal chance of being selected. A simple random sample. A great way to think about this, let's say you've got a room of 20 people and you need 3 people to make a group. Put everybody's name in a hat, pull them out, 3 names at a time, right? The 3 names you get is the group. Everybody's equally likely because all the names were in the hat, right? Totally at random. So simple random sample. Now that's not always feasible. So we have other methods. Because what if your study is on American citizens and you need 5,000 subjects? If you pick 5,000 random Americans, they're probably going to live in, close to 5,000 different towns and locations across the country. Not reasonable to test all of them. So we have other ways to make data more easily obtainable. The first is with a systematic sample. And here, every kth, K to the TH, think of it like first, second, third, fourth, fifth. K is just a random number, so maybe every 7th, maybe every 25th. Every kth subject is selected. You select every kth subject. An example of this, maybe you test every 200th iPhone for defects. If you have an assembly line with iPhones coming off of it, it's going to take you too long to test every single one for defects. So maybe you pick every 200th one and test it. You test part of them. Does this give you as accurate of results as a random sample? No, because you're only picking every specific spot out of the lineup, right? You're only picking specific numbers. Not everybody is equally likely. For example, if you're picking every 50th option, you might never pick Aaron out of your list of people because his name is AAR, right? Alphabetically, he would always be at the front of the list. So he might never get picked. So systematic isn't as good as random, but it's easier, right? You can just pick the 200th iPhone. Every 200th one off the assembly line, I grab it. So we use this a lot. That's one way of collecting data, right? Another is convenience. Here, you use the data that is easy to get. And we're going to have 2 examples. The first, door-to-door. You walk around your neighborhood going door to door and collect the data that way. Pretty easy to do, right? You just got to walk out the door and go to places. You don't need to select people. You just go door to door, knock on the door. Hey, you want to fill out this survey? Yay, nay. Pretty easy, right? Second example, we've already talked about this, but a voluntary response sample. Those are the call-in, the mail-ins, the polls, right? Where subjects elect themselves to respond. That's a way to get a convenience sample. You just, people choose themselves to complete the data. Now, those are the first 3, and they're all pretty different, right? One is just convenient, one is very systematic, every kth subject, and one is random. The next 2 go hand in hand. It can be easy to conflate the next 2 methods. So the first is a stratified sample. We divide population into groups and sample the same number of people or, items or whatever you're looking at. I use the word people here as a generic experimental unit, right? It's the same number of people from each group. An example, we want to divide the population of groups and get the same number of people from each group. Divide into male versus female and choose 25 of each. Maybe you're doing a medical experiment and the fact that you want the same number of males and females might be relevant, right? So you divide into male versus female and pick 25 of each. Maybe North Country. I want to get 5 students from every class at North Country. The population is North Country students. I divided it by class, and I'm choosing 5 from every class. I take the same number of people from every group. On the other hand, a cluster sample, we're going to divide into groups first as well. So the first step is divide the population into groups, then select some number of groups and sample all members of those groups. So here I divide into groups, and then I pick some number of groups and ask everyone in those groups. So an example, maybe I choose 5 city blocks and sample all residents on those blocks. So the population was divided into city blocks, right? You know, you look at a map of a city, you got a bunch of blocks, right? I then picked 5 of those blocks to sample. That's different than stratified. If I wanted to do the same thing for stratified, I would divide the population into city blocks and then sample maybe 3 people from every block. Here, I'm sampling everyone from 5 blocks, not 5 people from every block. Notice the difference. We used the example with North Country classes and picking 5 from every class as a stratified. What if I picked North Country classes as my population, and I chose 3 classes and sampled all students in those 3 classes? That would now make it cluster. Notice I can divide by groups the same way, but how I use those groups is the difference. So be careful. These two can be easy to goof up and get backwards because they both deal with dividing into groups first. So make sure you note those differences between stratified and cluster. The other 3 stand alone, right? Random, systematic, and convenience. Those stand alone and don't have another one similar to it, but stratified and cluster do. They do have a bit of overlap, right? You divide the population into groups first. So keep that clear in your head. And then lastly, types of studies. So we dealt with collecting data. Let's now deal with the time frame of a study. So cross-sectional, retrospective, and longitudinal are the 3 different time frames. I'm going to put little present, past, and future. Those are the 3 time frames we want to keep in mind, and in that order. A cross-sectional study deals with the present. All data is collected at the same point in time. All data is collected at the same point in time. An example might be asking each local 2nd grade class some questions. I want to collect data on 2nd graders. I go to Petrova, Lake Placid, Tupper Lake, right? I go to every school in the area and ask all the 2nd graders at the same point in time, right? I'm not looking at different years of 2nd graders. I'm just looking at 1 year, 2020, 2nd graders in 2020. Retrospective is past. Here, I use data from the past via records, interviews, newspapers, and etc., right? You're getting the data from the past. Maybe I want to collect data on World War I. Well, so an example on World War I data, reading archival documents to collect data on World War I. Maybe I want to know the average height of a person in World War I. Well, I can look at, World War I military records and collect that data. I can't measure World War I military people because nobody is currently serving in World War I, right? That happened more than 100 years ago. The data is not there to collect in real time. I have to collect it through past records. Now, a longitudinal study is a study done over a long period of time. A study done over a period of time. A study done over a period of time. We're collecting data into the future. An example might be surveying second graders now and every year for the next 10 years. For the next 10 years. So maybe I want to look at if there's any time differences related to when these students grew up. Maybe I think that this COVID-19 pandemic will have an effect on second graders in a few years. So I look over the next 10 years of second graders' data and see if there are any differences over the time period. Longitudinal, over a time period. Cross-sectional, one section of time, right? Retrospective, data from the past, think retro. That can help us remember, right? Cross-sectional, section. Retrospective, retro is past, like retro clothing, retro video games. And longitudinally, over a long period of time. Your time is part of the study, right? You're collecting data now and into the future. And so we have time frames as well. And that brings us to the end of section 1.3. Thank you for joining me, and I will see you next time.